Now, I'd like to introduce today's presenter, Geocomp's Massachusetts Consulting Lead, Antonios Vytiniotis. Antonios, would you like to introduce yourself?
Yeah, of course. Thanks so much, Jay, and thanks so much everybody who's attending today on this webinar. I'm the director of our mass consulting group in Geocomp, and our group here has been heavily involved in geostructural instrumentation and risk management type of work, and deep excavations are actually one of the types of geotechnical and geostructural projects that combine a few of our different practices. So um, today I'm really happy I'm talking about this subject that is quite complex. Now, uh, before we actually start the more in-depth discussion, I want to kind of just let you ponder for a moment, why do we care about deep excavations? And the answer is actually pretty straightforward. So deep excavations are actually an integral part of construction of critical infrastructure. What you see on the photos to the right, you see the construction of a linear infrastructure, and on the bottom you see a photo of commercial building infrastructure. In this particular case, you see a deep excavation that's partly supported by um, retaining walls and partly supported by on the open rock cuts. Now, the deep excavations are used in many applications. As we try to build in dense urban environments, deep excavations are needed more and more. For example, you see here a system for a high-rise building, and the deep excavations have a few key interesting characteristics that are very necessary to develop our projects, but they also have high consequences if something goes wrong with them. So I'm going to share you a few snips of some failures. For example, about 20 years ago, massive damage on a deep excavation in Nickel Highway in Singapore occurred, and we're going to talk a little bit about this at the end of this presentation. Another deep excavation failure was recently surfaced the news in about a project in Nanning, southern China, and you can actually easily find the YouTube video. You can see multiple levels of support bowing and allowing the soil to move. Another very famous deep excavation failure happened in DC in the 90s. That's a deep excavation investigated by OSHA at the time. Fortunately, there was no human loss during that. So, with that, deep excavations are necessary. Deep excavations are risky, but we know how to design these deep excavations, and we know how to construct them well. So with this seminar, my hope is I'm going to cover some general introduction about the systems. We're going to talk about some basics of their design, and we're going to cover some very specific challenges on deep excavations, how to manage the risk of these projects, and how to monitor the performance of these projects. And at the end of this webinar, after we've gone through the basics, I want to combine all these theories and practical guidance with 3 case studies and uh, just talk about some key takeaways. Now, in the middle of the presentation, there's going to be a few questions, and Jay will pop up a nice poll for you to provide your answers. So let's really start from the basics. So deep excavations have uh, are basically excavations that are more than a few feet deep, and because of that, we need to find some way to support the soil on the sides so that it doesn't fail through the open excavation. The support of deep excavations can range from structural walls with bracing or soil nailing. And these excavation support structures can be either temporary, that we only need them for during construction and then we're done with them, or they could be permanent. We need to perform this excavation support and leave it there because that's the actual long-term project we're constructing. The stability of these systems must be maintained on all stages of excavation, and that turns out to be a quite complex operation. And the thing that's also very important is not only controlling for stability, but is also very important to provide deformation control. Make sure that our support of excavation system does not move too much and adjacent structures also do not move substantially because of the performance of the support of excavation systems. Groundwater problems can also be quite significant because there's an open pit, and in many cases we create this open excavation beneath the groundwater table. So at its simplest form, a very simple way to support the soil on a deep excavation is via the use of cantilever walls. And one example of a cantilever wall is a soldier pile and lagging system like the one we see on the figure to the right. Another system that's commonly used quite a lot is a steel seat pile section. We can use structural diaphragm, slurry walls, or secant and tangent pile walls. An interesting thing to note is that these four systems that I just presented were mentioned in an order of increasing stiffness. Generally, shoulder pile and sheet pile tend to have the lowest stiffness, and secant or tangent pile wall systems tend to be the stiffer. The resistance and support of this system, as if you see my cursor, we have the dirt to the left that's being supported by this wall. And really the resistance and support is provided by the passive soil resistance on the embedded part of the wall. And the whole system is generally designed as a cantilever beam. Typically, we create these cantilever systems to support deep excavations that are not extremely deep. It's not very common to use this system for excavations deeper than 30 feet. Generally, the maximum excavation depth is controlled by soil resistance because this is what provides the support to our wall. Now, going past the cantilever walls, another family of systems that's used quite a lot are the supported walls. And one example of a supported wall is the photo you see to the right. And the supported walls can be braced, can have tiebacks, or can be supported by anchored bulkheads. And depending on the type of system we have, we may have compression supports. For example, in the wall you see to the right, the walls at the two sides of the excavation want to push towards the interior. Because of that, they exert some compression force on these braces. So these are compression supports. However, we can have also tension elements. For example, if we have tiebacks, the the elements can be temporary or can be really a permanent part of a structure. For example, if this deep excavation was part of a big basement building, the bottom slab of this building may actually be providing some long-term compression support for this particular installation. When we have anchored systems, there's many different designs, and those can have anything from lower to higher stiffness. And the anchors can either be grouted into the soil or they can be grouted within the underlying rock. When we have anchor systems, we typically need to estimate, we design them based on the expected soil loads, based on the construction sequence, but it's quite challenging to perform deformation control. And in many cases, an observational approach and monitoring the wall is quite critical. So let's focus just a little bit more on the braced excavations. So braced excavations is one type of support of excavations that the walls of the excavations are supported with braces, and this lateral support system may be braces on one level of supports or multiple levels of supports. And sometimes there can be bracing that goes across the entire lot. The three main geotechnical issues that we're trying to address when we do our design is number one, we need to design the bracing based on the maximum expected loads. Number two, we need to maintain the stability of the excavation at every single one of the stages of construction. And even if we have a structure that's stable and members that have strength higher than the required strength, we may need to control the deformations and their effects on the surrounding structures. Because of all these design issues, we generally need to have a very good understanding when we're doing our design, what are the actual methods of construction, what is the dewatering that's being performed, and the actual sequence of construction, and have a very, very good communication between the design team and the contractor team. So if I were to provide you a quick summary of some common systems that are used for deep excavations, I will start from the upper left side. This is the cantilever wall. This is really a cantilever beam embedded into the soil, and the soil provides the support. We can have single and multi-propped walls. And these lateral members provide the support, and they're pinned on an anchor point, which can be an anchor pin pile. We have a braced excavations with horizontal braces, many times extend from one side to the other side of the excavation. And as we go up to the right side, we can have anchored walls with the anchors generally embedded into rock or more competent soil. And we can have systems that, for example, the actual slab of a building that's newly constructed may be part of the support of excavation. So if you were going to choose an excavation, a supportive excavation system, there, hopefully a lot of you are familiar with DM7. It's a quite old document, but it's a very good reference. So DM7.2 has a few key recommendations on selection of support systems, and I'm not going to go through all of them. But for example, I want to focus on look at this row number 2. So one thing that contractors know generally how to do relatively easily is shoulder pile and seat pile walls, and these provide low initial costs. But if you remember our discussion that we had a few moments ago, this type of walls tend to uh, uh, tend to actually deform more compared to other walls because they have generally lower stiffness than other systems. Another interesting thing to note is that if you want to provide supportive excavation at deep soft clay type of site, it's really hard to get a tieback capacity, so it's not the right type of place to put anchors. You can still design them for them, but it's generally not going to be easy. Another thing that's important with the selection of the support of excavation system is how do they affect the groundwater table and lowering the groundwater table outside the perimeter of our project. And for example, if you look at number 7, one of the recommendations is that the shoulder pile walls are generally pervious. And that's something that you need to account for if that can affect adjacent structures. So let's start talking a little bit about the design of this system. So we know what they are, we know how they look, and their main function is to support the soil and support the soil in a way that may also need to control deformations. So the first thing we need to know to design these systems is what are really the earth pressures on a wall. And what you see on the figure to the left is a very famous diagram that describes what is the coefficient of horizontal earth pressures uh, depending on the scenario you're using and depending on the level of deformation. So if you actually are on the condition that your wall is moving away from the soil, this is the Rakin active condition. And if your wall is pushing towards the soil, the supported soil, this is the passive condition. And the horizontal passive earth pressures can be much higher compared to the active earth pressures for the same soil. However, you need different levels of deformation to reach active versus fully passive pressure conditions. And for example, one precaution that has been used traditionally is that the passive earth pressures you may be assuming for your design may not be accounted for fully, and there may be a safety factor applied specifically on the passive earth pressures to account for the fact that you need some more substantial level of deformation to activate passive earth pressure. So establishing the earth pressures on a single retaining wall with no struts can be quite straightforward. However, when you start to support a wall with different levels of struts, then this becomes a quite cumbersome exercise. So in order to address that, um, we use in our design, at least in our preliminary design, the concept of apparent wall earth pressure diagrams. And what you see here on this figure is you see the apparent earth pressure diagrams from Terzaghi et al. 1996, and this provides different diagrams for sands, and this diagram depends on the Rankine active condition coefficient, which depends on the friction angle of the sand. And you see this diagram for soft to medium clays in the middle. And one interesting thing is that this depends on this factor, delta kappa, which increases if we have more potential for basal instability when we support the clays. And you see a similar a diagram that depends on the unit weight of the soil for stiff fissured clays. So let's think about these diagrams a little bit. We as geotechnical engineers, we're very used to see these pressure diagrams that start from the vertical pressure diagrams that start from zero at the top of the soil at the ground surface and increase linearly to some depth. Similarly, horizontal pressures may have this a similar um, progression with depth. However, what you see in these diagrams is quite different. And the really key point to know about apparent earth pressures is that they do not necessarily represent the actual soil loads. They do represent the maximum soil loads that will be experienced at every level of excavation while the excavation is taking place. And they provide a locus of these maximum pressures that can be used for our preliminary design. So it's quite different from the actual Rankine active and passive earth pressures. So let's leap on that for a moment. Maybe we can pull up the next poll question. So just to make sure this concept is with you, what do these apparent earth pressure diagrams for pressed excavations represent?
Yeah, Antonio, so you did not have this one listed as a poll question. So if you want to just give the answer for it.
Okay. Well, okay. Yes. So they really do represent the locus of maximum um, earth pressures experienced at every strat and what we can be using for our preliminary design. So on top of the soil loads, then we need to consider a lot of other things. And one thing that you see here on this slide in DM7 um, coming from in this plot coming from DM7.2 is the earth pressures that could be exerted on a wall due to surcharge loads. And what this plot is telling you is that if you have a load, let's say a line load or a point load next to your retaining wall at some specific distance, this will be the additional level of horizontal pressure you will see exerted on your retaining wall. And that's something you need to take into account. That can be easier or more complex, and if it's more complex, that's a situation that a simple diagram like that may not be sufficient. And another thing that's quite common in both sands and clay sites is you need to make sure you account on these deep excavations for your stability of the base of your excavation. And if we're talking about sands, this figure here coming straight from DM7 is there to help you estimate preliminarily a factor of safety against heaving in loose sand or piping in dense sand. So based on the ratio of the length of your seat pile to the height of your excavation, and based on the ratio of your width of your excavation to the groundwater head, you should be able to estimate for either a loose sand or a dense sand an approximate safety factor. In many situations, you may require a more complex solution or a finite element analysis. If your retaining wall is in clays, then you expect a much smaller seepage going into your site. However, in clays, you may have to account for basal stability, and you may need to even use a slope stability software to evaluate that. And then there's a lot of internal components on the wall, on this supportive excavation walls you need to be designing for. And I'm gonna just briefly mention here some information about anchor and tie rod design. So as you see here on this sketch, over here, there is a retaining wall that supports the soil to its right, and you can see a potential rupture surface of active wedge. So the main recommendation, if you have a tie rod, the anchor of this tie rod should be outside the rupture surface, outside the active wedge. So that's a non-brainer. And at the same time, it should have the adequate capacity. At the same time, the actual anchor block should be designed in a way that supports the tie rod expected loads. And the anchor block can actually be designed quite straightforwardly. This is a little bit of a busy slide, but I want you to focus on just a few very key things. So if you see the figure to the closer to the bottom, if you have a dead man, then as this dead man gets pulled to the left, this will cause some passive wedge resistance from the left and some active wedge push from the right. And if the ultimate capacity of the deadman is essentially the total passive earth pressure from the support side minus the active earth pressure from the acting side. Okay, so with that, I hope you just try to scratch the surface of how complicated deep excavations can really start to be. And then if you start to really consider the appropriate soil constitutive behavior and the complexity of the structural systems and the soil structure interaction, some of the answers you will want for your design may not be easily obtained by simpler solutions. And one One way that's used more and more these days is to perform finite element analysis of deep excavations. And there's quite a few challenges when we use finite element analysis. And one key issue is modeling the appropriate constitutive soil model response. And we can have a lot of different soil responses and soil behaviors that may be useful for our analysis. We may need to consider the drain response of the soil, the undrained response of the soil. We may need to consider partial drainage and flow, and we may need to consider partial saturated behavior. Then the other part is to appropriately model our structural performance. If we create a model of a deep excavation, we need to have enough complexity that the structural system is sufficiently modeled. And then we need to know that the soil structure interacts in a way uh, in our model that's appropriate and realistic. And in its simplest form, we may need to provide the right frictional interface of structural components and the soil. In some other situations, we may need to provide the TZ response or PY response of pile elements. And again, as we mentioned a few slides ago, the construction sequence, all the construction activities that are going on, including dewatering, waiting times, are really very important, and we need to make sure that these are simulated appropriately. One of the uses of finite element analysis is really to control for displacements. And what you see here is analysis performed by Clough et al. At 1989. And this figure is quite insightful. And it shows on the x-axis that it has a measure of the wall stiffness. And the wall stiffness increases to the right. And it also has a measure of the maximum lateral wall movement normalized by the excavation depth, and that increases as we go up. What is very interesting to see, number one, as you expect, with increasing system stiffness, you get smaller lateral wall movements. Okay, that's expected. But what's interesting is that there is a substantial effect of increasing system stiffness uh, as we move from sheet pile walls to other systems that are much more rigid, for example, slurry walls. Now, this type of output, as we see, is also controlled by the factor of safety against basal heave. And the bigger factor of safety you have, the smaller deformations you're expected to get. So a chart like that is quite useful to get a preliminary assessment of what will be the wall movement based on the system you're designing, and use that to preliminary assess, is my system the one that's going to perform the way my requirements are set for this particular project. Okay, so now deep excavations, as we said, they're big operations. They involve a lot of time, a lot of construction activities, and they're complex. And because of that, it's quite important to be able to analyze the risks of them as construction projects. And just to give you an overview, what I call risk management here is a systematic approach of identifying, analyzing, planning, monitoring, and responding to project risk. And the way to do that is you can do that with processes, tools, and techniques that you can minimize the probability of consequences and adverse events, and also maximize the chance that good things happen, positive events. So a few fundamental things we need to be doing when we're thinking about risk management is we need to know what the risks are and what are their potentials in cost, schedule, quantity, and we need to eliminate, mitigate, or avoid risks when able. Uh, we need to have a plan and communicate that frequently and widely, and we need to have something quantifiable to measure. And that could be some key risk indicators. And as we're able to measure these indicators, we need to find a way to mitigate these emerging risks. So some key actions on performing risk management in general, and then we're going to talk about specifics on deep excavations, is we need to, number one, to plan a risk management. How will the project approach the risk management? We need to be able to identify the risk events. We need to be able to analyze them. And in some cases, we're able to qualitatively analyze the risks. Some others, we have the opportunity to analyze them in a quantitative way. We need to develop a response. And as we discussed, we need to monitor and control. And then we may need to go back on our drawing board and update our risk management system as the project moves along and some parameters change. Now, in a few large projects, we can find some similarities. And number one, that the bigger the project, the less likely one or two people can really get their arms around a balanced assessment of risk. And the contractors generally price the risk. They may understand that there is risk and they may increase their price to do a more risky job. But one thing you need to be thinking is, do they have an objective and even quantifiable approach to do this? Sometimes various contractors may choose to transfer the risk from one to the other, but this transferred risk is not really reflecting a reduced overall project risk. And sometimes competitors on joint rescue venture teams don't talk openly. So when we have shared and open risk reviews, this can be a great planning and communication tool that can be very useful. So when we take care of our risk and we manage it, we're able to reduce the project cost and delays. We can create a systemic balance framework to identify, communicate it, and manage it. We can provide an independent assessment of the risk that doesn't have internal biases. Some entities in construction projects choose to do their own risk assessment, but that's bound to have some internal bias. With risk management, you can provide a rational and transparent basis to establish, monitor, and even release contingency budgets. And if you manage your risks well, you can really avoid surprises in budget, schedule, or any other losses that could be important. So specifically, in deep excavations, there is a few key considerations that make deep excavations quite risky. Some of the things we need to be thinking is, number one, can the deep excavation system fail? And that could be anything from a bearing capacity, basal stability, or global stability failure, or it can be a structural failure. Then we need to be thinking damages to adjacent buildings caused by deformations or other contributing factors. We need to be thinking the groundwater control inside and outside the excavation. And we need to be thinking a lot of a series of other issues, such as potential for loss of productivity, delay, or even loss of life. So if I were to show you a quick visual of how some key failure modes in deep excavations look like, you can see a series of structural potential failure modes, such as the struts failing out, the connection failings, or actual buckling of the support, or the wall may actually fail in bending, axial loading, or shear. And then this figure also has a few geotechnical type of failure modes, which could be bearing capacity issues of adjacent structures, global stability, bearing capacity of the wall, especially if that temporarily or long-term supports other loads, or a potential for a seepage uplift. And we discussed that quite a few. Now, one of the common effects that's being discussed, especially in urban environments is the effects of deep excavations on adjacent structures. So with this brief sketch over here, I'm showing that once the retaining wall moves laterally, and generally in most situations, a retaining wall will move to some extent laterally unless there is an extremely tight deformation control. And as this occurs, the soil will move also laterally and vertically, as you see on these plots. And if there are buildings placed above that soil, that can cause differential settlements or total settlements that can contribute to damages within the building. This could be structural damages, or they could even be mechanical damages and affect the instead of the actual superstructure, they may affect the piping connections, the water connections, or even stormwater drainage within that building. And the question you may be asking, how important is that effect? Well, these deformations have been, next to supportive excavation systems, have been measured over and over again. And as you see in this figure to the left, these are a series of real data measured in a few different sites. And you can see most of the deformations occur very close to the retaining wall. And once you exceed about one height of uh, the uh, the distance equivalent, a distance equal to the depth of the excavation, then you expect smaller deformations occurring within the soil, but again, they're not negligible. So this is established over and over again, and Boskardin and Cording in 1989 also published this very interesting chart that shows how angular distortion that you see on the x-axis and horizontal strain uh, correlate with damage to various buildings. And you can see, for example, the building settlement is generally along this line, and you can see how increasing angular distortion will cause substantial differential settlements, and it can cause severe damage after we exceed some threshold limits. So all of these are very important, and because of number one, of our need to optimize our design and our need to also control the risk of deep excavations, we like to monitor our deep excavations. So generally, what we want to be doing is we want to accurately predict lateral soil loads, structural forces, moments, and soil deformations. Because even though we do our best as design engineers to appropriately represent those conditions, the actual field scale experiment of constructing the site is the one that's going to be also very insightful to help us see if we need to update our design assumptions. So in order to do that, we need to establish and monitor some key performance indicators, some things that we can quantify, measure, and use them to review our design. So we need to be prepared to adjust design parameters and potentially use the observational method. So some key performance indicators that are generally being used is what is the lateral wall deflection, what is the soil settlement and lateral movement, what are the stresses within the struts, the anchors, or any pre-stressing wires, what are pore pressure changes within the soil, the potential movements in adjacent buildings and utilities, and we may need to control for vibrations due to construction activities, which could be anything from pavement breaking when the project starts, or pile driving, if that includes some shoulder pile installation. Now, luckily, we do have quite a lot of instruments to use these days. So I'm going to go through quite a few of those. Uh, the uh, Here at Geocom, we have experience with a great variety of these sensors, and we actually have used them in a lot of our projects. And the one key interesting thing that these days is quite easy to do is we don't, for a lot of these sensors, we don't necessarily have to have staff go and monitor them every day. We can automate data collection and be able to have valuable insights arriving almost real time and be able to check our design and provide risk alerts and alarm levels if necessary. So a few of these instruments that we like to use are number one, inclinometers. They're used to measure horizontal displacement on the soil, and they're generally, this measurement is done by lowering a probe into the flexible vertical casing. Then we do have piezometers that they monitor pore water pressure into the ground, and there is a variety of piezometers. We can actually monitor pore pressures in observation wells, in standpipe piezometers, pneumatic piezometers, or vibrating wire transducers. And one of the key questions we may need to answer is, do we need to monitor pore pressures throughout the entirety of a soil layer, or do we need to focus to a very narrow, thin zone? Settlement plates are used to monitor change in elevation of a plate buried within a field. Tilt meter, like this tilt beam that I show on the photo to the left, is used to measure rotation of a structure from vertical. For example, it may be very useful if you have a structure such as a pylon that sees a lot of lateral loads due to wind. You can see its performance during various type of storm and hurricane events. Another instrument that's used quite often because it's cheap, simple, and effective is crack gauges, like the one you see on the left. Crack gauges are very commonly used when you want to evaluate the potential growth of cracks on buildings. So if you want to evaluate the potential effects of a deep excavation and you have adjacent properties that already have cracks, you can install this crack gauge, and you can see by looking at this red line um, if that crack gauge, if that crack opens up or moves over time. Can also be using extensometers, which are used to track slope movements or failures. Some instruments that you can use also on the structure are strain gauges. You can put them, for example, on tendons or braces, and you can evaluate the change in stress experienced by a structural element. You can also use load cells to measure force in a structural member. For example, you may even be able to use a load cell to measure the actual soil load on your wall. And then you can use accelerometers or geophones, which are velocimeters, to determine dynamic effects on a structure, or to actually determine the measure velocities within the soil. And a common way to assess potential for vibration-induced damage to adjacent structure is to make sure that the peak particle velocities you exert in your construction do not exert some limits that are set based on the type of structure and type of geologic conditions you're dealing with. And liquid level gauges are also commonly used to measure the change in elevation of a point located along a horizontal liquid field pipe. Automated total stations are used to measure distance, azimuth, and zenith to a reflecting target. And one of the really cool kids on the block that's used more and more these days is the INSAR data, which are interferometric synthetic aperture radar. It's not a instrumentation per se, but it's a remote sensing technology, but it belongs to the wide category of things we can use to measure performance of our deep excavations. This is an example of INSAR data. These are data based on collected by satellite that are able to provide information about surface change over large areas. And the benefit of that is we have a lot of historic data. So even if there's no sensor installed, sometimes INSAR data can be used to look back into the past and see historical performance. And another thing that's commonly used is LiDAR, which allows to create precise contour maps in the surface of the Earth. And again, the latest kid on the block is pushing LiDAR away because a lot of people are starting to use photogrammetry, which is much cheaper, simpler, and it started to provide contour maps of the same accuracy as LiDAR. And just very briefly, this is just an instrumentation example that we at Geocomp installed. It shows you how easy and tidy some of these installations can look like after you're done. But there's a lot of complexity in making sure that all of these sensors are done right. What you see here is an installation that has solar power, GPS receiver, cell modem, and it includes inclinometers, extensometers, and tilt meters, all of them organized and automatically streamed on our data collection website. So with that, I want to briefly go now, the next 5 minutes, to 3 case studies. So number one is a few years ago, we worked monitoring the LA Metro tunnel and deep stations construction. And we provided real-time performance monitor of a variety of sensors. But the real key thing I want to talk to you about today is that in one of the stations, the station that you see on this photo circled over here, the engineer predicted a ground loss, a ground settlement of about 1 inch outside the station. And we did an extensive performance monitoring, and we were able to show that the dirt actually heaved 0.6 inches. So the city was really questioning that, and they were very curious why these measurements were so different than predictions. So this is a better overall of the entire station, and uh, the key figure that you see here is a bunch of points annotated in the perimeter of the excavation that show measured consistently measured here. And not only that, but this is another chart that shows you from January of 2015 all the way to January 2016, an incremental heave occurring in a series of sensors. So it wasn't just a unique event, and it was a general trend. So what was going on? Well, a typical deep excavation, you may see that the soils are soft, so you excavate, you may expect the soils to move. In this particular situation, the soils were very strong. In a typical deep excavation, you may expect that the groundwater is very shallow, or there will be some level of dewatering occurring, and that will cause additional settlements. Well, in this case, the groundwater was pretty deep. Also, in many cases, you may have a support system that is relatively soft, such as a sheet pile wall. The system on this particular situation was very stiff. So if you take out the 3 main reasons that cause settlements next to deep excavations, then the only other big mechanism that's really happening is you excavate the soil, so you unload. So because of this unload, the only thing you can expect to happen is heave. So the effect of unloading was much more substantial. So that was a very interesting finding. Well, case study number 2. This is a case study that we got permission to reprint from Structure magazine, and it involves the Nickel Highway collapse. And this was a excavation that was about 100 feet deep in deep layers of soft marine clay. This excavation collapsed on April 20, 2004. Now, The interesting thing about this collapse is that a finite element software was used for the finite element design. And the software allowed the design engineer to model undrained behavior using effective stress parameters. The design engineers took advantage of this and modeled the undrained conditions using effective stress parameters with a constitutive model, more Coulomb, that was not appropriate to do that. So what was the consequence? If any of you know about stress path, this is on the PQ space. If you load up a sample in an undrained mode, you will expect to reach the failure envelope at this point over here, and this will represent the strength of the soil. However, the more Coulomb model makes the soil, the undrained response that it predicts is a vertical line that hits the failure envelope in a much higher strength. Hence, by doing that, the engineers overpredicted the soil shear strength, they grossly underestimated the forces and moments, and they failed during construction to accurately understand this in order to do something about that before that collapse. That's number two. Number three, another quick and interesting case study is a failure that happened now more than 30 years ago in DC. It's a 47-foot deep open excavation, and OSA created a very nice investigation report out of that. You can see that this wall consists of 3 tiers of internal bracing at the east side where the first collapse occurred, and you can see how the collapse looks like. You can even see how the dirt stands vertical for shortly after the collapse occurring. So the main finding of this is that that really highlights the need to have geotechnical and structural engineering disciplines to work well in a geostructural type of study that integrates everything. And the collapse of this excavation really occurred due to failure of certain structural members. Um, and some external support systems, such as tiebacks or shoulder beams in the west wall, really did not fail. And it was found that generally the soil pressures agreed with the expected loads. And not only that, but the soil load during failure was actually lower than the expected load for which the structure was designed. However, based on these design soil loads, which were actually higher than the real loads during failure, some of the structural components, such as the wale at the south wall and some walls at the east wall, were not properly proportioned for these expected loads. So it was purely a structural failure uh, caused by the lateral soil loads. And the groundwater pressure in this particular case or construction defects really did not have a substantial contributing factor to this failure. So some key takeaways is we commonly need deep excavations in our large construction, especially in urban environments. This can be complex to design, especially when we have multiple levels of supports or soft soils. Um, and this is something, a construction activity that frequently can encounter complexities that cause delays, increased costs, or damage. However, by doing smart design and doing risk management and instrumenting and monitoring our construction, we can, number one, optimize design, provide a project to a lower cost, and increase the safety of our system. So with that, I know we're maybe 1 or 2 minutes late, but I can take maybe 1 or 2 questions. And of course, I welcome any questions, or if you want to email me, I'll be happy to respond.
Yeah, so thanks, Antonios, for powering through that. I know you've been feeling a little under the weather, but you did a great job. Yeah, so we had a couple of questions that popped up in the chat as the presentation was going on. John Martin asked, is DM7 part of the NAV FAC design manual? That seems very specific, but maybe you know what he's talking about.
Yeah. DM7 is the NavFAC basically manual.
Okay.
Yeah. And actually, I'm very excited because one of the DM7s was recently updated. I downloaded it maybe a month ago. I want to say this is DM7.1, which I'm not sure if that's the one that talks about deep excavations. But I kind of urge everybody there to just download the latest and greatest. It has a very interesting section on selecting soil properties for analysis. And I really want to dive a little bit deeper on that.
Awesome. And then Rajan asked for you to comment on geotechnical lab testing. And for soils, what do you consider to be important for proper analysis and design of deep excavations?
Well, that's a very general analysis. So it really depends on the type of project, the type of material, and the consequences of the project. So it can be anything from there are walls that can be designed with a simple SPT test if all we need to is to know the density of in situ materials and some reasonable approximation of the friction angle. But there are situations, especially in much more complex excavations, if you were to do 100-foot deep excavation in soft soils, it's very likely you may need to do some advanced undrained testing. You may need to pick up some Selby tubes and make sure you know the strength in different levels of anisotropy. You consolidate them at the appropriate stress level, the C at the site, you minimize disturbance, and you measure the real actual strength for the type of shear plane that's activated on your wall.
And then we had one more question regarding the instrumentation example slide, and they were kind of wondering why there were GPS elements in that slide, and maybe what's the reasoning for that.
There's a few things. So GPS is useful to know where your sensor is, number one. Sometimes GPS is also useful to get a time stop, and you can use that time stop to coordinate between different sensors that record various time-sensitive information. And there can be other reasons that our instrumentation group may know also.
Awesome. And then one more question just came in that I thought was a pretty good question. So how do you decide on tolerable deformations? What would be a tolerable deformation?
Well, it depends on the type of the building that you have. So there's quite a few literature on based on the specific building you have, what will be tolerable, and there is a lot of things you need to consider. For example, a well-constructed reinforced concrete building that's relatively new will be able to take more differential deformation before it starts to see conditions. Um, Brick stone building that has a rubble stone foundation, it's more likely that it will start to show some cracks between the stones with a smaller level of deformation. And again, the consequences are different. If you have a basement with a rubble stone wall, even a small crack may immediately cause water ingress, and that's something you don't want. If that rubble stone is above the ground, and the rubble stones will move a little bit next to each other, you may see a small cosmetic crack, but this doesn't mean anything, and you can still go in and patch and repair.